Hi, my name is Autumn McSwain, and this is my GaTech Physics 1, the Falling Slinky lab. So, the purpose of this lab is to use learned physics principles to determine the motion of a slinky that is falling from rest and analyze what occurs in the surroundings. Due to this, the slinky will be the system and everything else will be in the surroundings. The methods for this lab was to first use the video given and import it into Tracker to be able to find the observed position as well as other things that may be needed. Next, we use the data we collect from Tracker and we put it into GlowScript to create a computational model that will be used to determine the ideal motion. With these two, we will then compare them to be able to determine whether the bottom of the slinky stays still throughout the entire model. And the results end up being that this slinky bottom seems to stay mostly still until all of the other parts make contact with the bottom of the slinky, forcing it down. So, some fundamental principles used is Newton's second law, which states that the acceleration of a moving object depends upon the mass of the force acting on it, which is the formula F net equals delta P over delta T. From this, we were able to get the velocity update formula and the position update formula, which will be used in this lab, where Vf equals Vi plus F net divided by mass delta T for the velocity update formula, and then the position update formula is Rf equals Ri plus V average times delta T. Next, we will use the drag force, which is the resistance experienced by an object as it moves through fluid. In this case, the fluid will be air, and that's given by Ft equals negative B V squared V hat. Finally, we have to understand gravity and tension. This is because the slinky will act as tension and it will oppose the force acting against it, which will be gravity. This is shown in the diagram where Ft will act up and Fg will act down, which is why Fg is negative and Ft is positive. So next, we imported this video into Tracker. It was a given video, and you can see the axes that I used and how it all fell. This is as it was in motion. So where the slinky is right now is where it was halted throughout the entire experiment until it hit and then dropped. And it was dropped from this man's hand. So the mass was given to be 0.218 kilograms for the slinky. The drop height was the height of the man, which is 1.75 meters, which gives us an initial position of negative 1.632 times 10 to the negative third, 2.725 times 10 to the negative fourth, 0 meters, and then the initial velocity will be 0 because it was dropped from the man's hand at rest. So we then take all of this data and we import it into GlowScript to get the ball's mass to be 0.218. We then have the ball's position vectors and ball's velocity vectors, which are just the two before imported in. The clock also starts at 0, and the force of gravity is 9.8, which is imported. The thing of importance is the drag force at the bottom, which we've used it to be B equals 75. This was just trial and error, and that's how I found that one. So next for the code are the loops. So the loop on the top is while the bottom of the slinky is still. So until 5.53, the bottom of the slinky is constant. And then we have the net force, which is given by the gravitational force, which is W equals negative ball dot M times G hat. And then the slinky slash tension force will be the Ft equals negative W. So then F net will equal the force of gravity plus the force of tension. Below it, we have the ball velocity update formula, which will update the velocity as it moves along. And we have the position update formula, which will update the position as it moves along. And then in the bottom set of code, this is the set of code where the bottom of the slinky is moving towards the ground. So this is the time it takes for the slinky to reach the ground. So the gravity is still mostly the same. However, we are no longer using the force of tension. We are now using the force of drag, which will be negative B times mag ball velocity to the second times the normal ball velocity. And then we will once again use the velocity update and the position update formula. Now, the Ft changes to Fd because Ft is the force of the slinky, which is what's holding, or which is what's holding the bottom of the slinky still. However, once the top of the slinky hits the bottom of the slinky, the whole thing begins to move, which causes it to drag. So these are my results. As you can see, the predicted and observed are very similar, with a few mild errors as it continues to go down. Now, reasons for this could be that Tracker is just not accurate. It is not an accurate software, and there are a ton of issues with trying to track it via auto tracker or just with manual. So getting the same spot on the slinky consistently is really hard. The other reason for error could just be other forces, because in real life, the system was not isolated from the outside world. In fact, they did it outside. But in the GlowScript, it was isolated. So those are some reasons for error. This leads me to my discussion as why does the bottom of the slinky not move? This is because the force of gravity is canceled out by the force of tension the slinky has due to its spring-like nature. This means that as the slinky is dropped, all the individual pieces of it will move independently from the bottom until it hits the bottom, which is why it is able to stay still and fall. Now, would attaching something to the bottom or top of the slinky change this? Top would not really, it would just make it fall faster, so you would not see this phenomenon as well. However, if you attach something to the bottom, it would change this because that would add more weight, which would overpower the tension force of a regular slinky. So in order to overpower a weight on the bottom, you would need something that has a large enough tension force to counteract this, which could be done by having a larger slinky in general or one that is longer. So you could have one that its diameter is longer, or one that has a bunch more pieces to it to make it longer. And that's the only way to cancel out that tension force. And that is my Lab 5 Slinkies, the Falling Slinky. Thank you for watching.